Okay, anyway, so if you buy that the indistinguishable molecules case is the problem to solve, this is the probability density function. So in other words, this is f of received times, in other words, the times that are measured by the receiver, given transmission times, the times when molecules are released. So it's this big, fat, ugly thing, but the important things to note here are that this is the first hitting time distribution. So this is the first hitting time distribution of y of some pi I, given that the ith molecule is transmitted at this time. However, this sum is over all possible permutations of that. So the issue is that for each transmission time, you have to account for the fact that this transmission, that each arrival could have arisen from that transmission time. So this is a sum over all possible permutations of the arrivals given the transmissions. Like I said, they can occur out of order. So the issue is that that's intractable for any practical number of particles. This is related to a mathematical object called the permanent of a matrix. And there's no unlike the determinant, which is closely related to, there's no efficient algorithm to calculate this for a large number of molecules question.
Do you have an extra causality assumption in your model?
Yes. So you can force some of these terms to be zero because they're causal. That's right. Unfortunately, it doesn't shrink the dimensionality of the problem enough. It sometimes works and sometimes doesn't. Okay, that's a big fat bummer. So we can't calculate mutual information exactly, but what can we do? Well, mutual information can be written like this as an expectation. So maybe we can do something like Monte Carlo, but we can't really do that because what's intractable is f of y given x. So by Monte Carlo expectation, what I mean is it's easy to generate x and y. So this channel is very easy to simulate but hard to analyze. So what we can do is we can generate lots of x and y and calculate this expectation empirically. But f of y given x is the thing that is intractable. So what I can do instead is find a tractable approximation to f. So if I find a tractable PDF, it has to be a PDF, G, which is an approximation of f. And it turns out, I mean, certainly I can write this if it's a good enough approximation, just substituting G in for f. It's clearly, if it's an approximation, then it's got to be close. But what else is interesting is that there's a very old theorem that states that if you do this for any G that has these properties, what you actually get is a lower bound, a lower bound on mutual information. So that's where I was coming from with the bounding. So assuming that all of the molecules are distinguishable, you get an upper bound. You're doing it this way, applying this approximation, you get a lower bound. So eventually what I want to do is I want the gap between them, I'm not going to show them in my results, I have them elsewhere, but the gap between them is considerable. It's about an order of magnitude, so eventually I'd like to close that. This is actually quite a simple, the proof of this is quite simple, but it's relatively obscure. I wasn't aware of this until I actually derived it myself, put it in a paper, and someone said, oh, by the way, this has been known for 40 years. So, yes?
So the x and y, are you treating it as it's not a discrete number less than, right?
No, not at all. In fact,
x and y is at a vector level?
Yes, so x and y are both vectors. X and y are vectors of, x is a vector of times when you release molecules, and y is a vector of times when you observe molecules. So in other words, x is the thing that the transmitter is doing, and y is the thing that the receiver is doing. Okay, so what's a good approximate model? Well, the simplest thing you can do is force this channel to be discrete membranes. What we're going to do is we're going to count, in fact. So we're going to discretize time and say that the only times when we're allowed to transmit molecules are at the beginning of those intervals. And then what we're going to do is we're going to count all the arrivals inside each interval. So, for instance, if I release something now and it arrives within the time instant, or it arrives within the time quantum, then I will certainly count that transmission. On the other hand, if it doesn't arrive in time, it'll be, I'll call it lost. I'll disregard it. So what I'm gonna, what my observation will be composed of is the true arrivals. In other words, if I drop a molecule and it arrives in time, and also all of the lost particles that are floating around in the background that eventually arrive. So what my idea here is that I drop something here and it either arrives or doesn't arrive within t seconds. If it doesn't arrive, I ignore it. And then I treat this background arrival process as an independent noise process. So in other words, this is now, I've forced this model into a discrete memoryless channel. In every time instant, I'm counting the number of arrivals and I'm treating them as independent, even though they're not. So that's clearly an approximation G, and clearly I can use that in my approximation to come up with a lower bound of neutral information with the system parameter PA. In other words, the probability that a particle I send will arrive within t seconds. Okay, so I have results, just very quickly, for motor-driven propagation in confined channels. So firstly, what we need is the first arrival time distribution. And that kind of looks like this. So this is for, like I said, when you drop a motor into that channel, it has polarity, so it will either start out traveling towards the receiver or directly away from the receiver, in which case it has to turn around and come back. So that's why these are bimodal. So basically what you do is you simulate the channel with thousands and thousands and thousands of these motors and come up with a first arrival time distribution empirically like this. So this is for a length of the channel that's 10 micrometers, 20, and 30. And using my very simple approximate arrival PDF, these are some neutral information results. So this vertical axis here is bits per second. And the horizontal axis here is, because I'm assuming a discrete memoryless channel, I'm assuming that the input distribution of X is also memoryless. And so therefore this is the probability of X. So this is the probability of releasing a molecule at any given time instant. So we see there's a peak over here somewhere. The important things to take away from this curve are that, firstly, the time rate of communication is unsurprisingly very low. So it peaks out at about half a bit per second. In fact, significantly less than half a bit per second. That's not super surprising because lab-on-chip processes tend to be very slow. They're measured on the order of minutes to an hour. There's still an improvement over sending something off to a lab, which would take days. On the other hand, if you consider this in terms of bits per molecule, the rate is surprisingly high, or bits per transmission, bits per microtubule in this case. So for instance, over here, this is transmitting every 10 channel uses on average. I send 1 microtubule, and I get a time rate of about 0.2. So if I divide 0.2 by 0.1, I get bits per microtubule, which is about 2. So that's, for a tiny amount of matter, you can send a considerable amount of information.